we'd like to prove that a convergent sequence is a Cauchy sequence. So let's write this down. So as a reminder, we'll define what a Cauchy sequence is. So a sequence, let's say xn, is a Cauchy sequence if, so for all epsilon greater than 0, there exists an n in the natural numbers such that the absolute value of xm minus xn is less than epsilon whenever m is greater than or equal to n is greater than n. And this, let's undo that. This part can be, well, it's equivalent to saying that m and n, well, it's equivalent in this case, that m and n are greater than n. So let's go ahead with the proof. So we start off with xn being a sequence that converges. So let xn be a convergent sequence. Then what does it mean for xn to converge? It has a limit as n approaches infinity. And we'll define this to be the limit L in this case. Now, we want to let epsilon greater than 0 be given. And we want to let n, so we want to kind of have a condition on n so that this proof will work. So let n be such that, so we want the absolute value of xn minus L to be less than, this is a careful choice and an intentional choice of a bound, and we'll see why this is appropriate as we proceed. And we want this to be true whenever n is greater than n. So after the point capital N in the sequence, we have that the absolute value of xn minus L is less than this choice of bound for every point after the point x capital N in the sequence. And how do we know that such an n exists? So as an aside, I'll just write that we know such an n exists since we know that our sequence xn converges. Now, if m and n are greater than n, then let's construct this as such. So we want to take the absolute value of, I guess, the difference of 2 points in the sequence, the points xm and xn, and we want to manipulate this in this kind of way. So we'll subtract and add the limit that the sequence converges to, and we'll see why this works in this proof. So next I'm going to employ the triangle inequality. So I'll just write out what it is in general. So when you have the absolute value of a plus b that is less than or equal to the sum of each absolute value. Now, knowing that, we can say that what we have here is less than or equal to xm minus L. We close that up and open another absolute value. And we've just used the triangle inequality there. Now, consider this absolute value here. We know that L minus xn is equal to xn minus L. That's just a general truth of when you're taking differences inside the absolute value function. So we know that this is strictly less than, so let's have a look at our choice here. So we've chosen to be, for the absolute value here to be less than epsilon on 2. So we can take this this part to be strictly less than epsilon on 2 plus epsilon on 2. And why does it work for the mth value of the sequence? Because we have m and n greater than capital N. And if it's true for n greater than n, then it's definitely the case that the size is less than epsilon on 2 for any point after the capital N in the sequence. So now we have this. And this we can say is equal to epsilon. So note that our choice of bound here was helpful in this construction, because by taking the triangle inequality, we end up with the sum of these two values here, which gives us the epsilon that we're after in the end. So let's just rewrite this working in one line. Ooh, that's not quite right. So what have we shown? We have shown that when the sequence xn converges or I should probably write it like this, when it is convergent, we can find some n, so some point in the sequence. So with what we have shown here. And this is true for all epsilon greater than 0 as it was given in the proof. And whenever m and n are greater than n. So that completes the proof that a convergent sequence is a Cauchy sequence.